we shall use the notation m of epsilon is infimum over x of the expression u minus 1 minus epsilon times v. Epsilon is small and positive. Then there exists a constant c, which depends only on n, on the dimension, such that for any s in the interval, again very small interval, 0, epsilon to the power 3 over some number depending on n. We have this is the set of which we integrate. We take the Monge-Ampère equation, Monge-Ampère operator related to 1 minus epsilon times v. V is the same as before, epsilon to the power n. And we integrate here over the same set. So, what is better is that we don't have those terms, but we have to perturb v. We cannot take v like in this case. We have a more complicated set here. And again, this is useful if this constant is close to 1, which means that this s must be very small. It only works for small s, and then it can be used when you gain something. Maybe I will just sketch a proof of the first version. The second version is more technical. So first we have a lemma which is a part of the original proof of Bedford and Taylor, so I will not prove it here. U and v as in the statement. We take t to be omega u1 wedge omega u2 wedge up till omega un minus 1, where uk are bounded and omega proves the harmonic. Some functions like that. Then the dc of u minus v wedge t over the set u smaller than v is bigger or equal dc u minus wedge t over the same set. Well, why this is true? You apply Stokes, and there is one more term, the boundary term. The term where when we integrate over the boundary of this set, and then we have dc of this difference, wedge t. T is a positive current, and if this is the boundary, dc points outward. And this function is negative inside and positive outside, and then you can compare this current with the surface measure over the boundary of omega, and you get that this boundary term must be positive. Okay, so having this lemma, we compute. This is just by writing this omega v is omega plus the dc. That's and now we apply the lemma. was, and we apply the lemma to the second term, getting two more terms. Like this. The same set plus this is equal. We take the first two terms together, and then we have omega u plus omega v to the power n minus 1. Here we switch d and dc, which just changes the sign of this guy. We apply Stokes to the second term. Let's go here. The function here just by supremum. Okay. And this DDC of this, for the bound for DDC of this, we applied those inequalities. Because if you differentiate, if you apply d and dc to omega v, DDC of v is closed, so you don't get any terms. You only get terms where you differentiate omega, and differentiating omega, either you differentiate twice and you get DDC of omega, or where twice the same omega, or you have this. And those two guys are bounded by those expressions. So, in effect, we get something like this: omega squared, omega to the power n minus 2 plus omega to the power 3 omega times the constant b here. Okay, and this is just the first step. What has been done in this current, we replaced at least one omega v by either omega u or omega. And then we have to repeat it n minus 1 times. Just to get this. You see, in the first step, we got the polynomial of degree 1, right? So this is the idea of the proof of comparison principle. And now let me pass to the equation itself. Okay, so we want to solve the equation. Where f is in Fp of x p. But now there is a constant c which does not appear in the Keller case, because in the Keller case we take just sufficiently normalized, well normalized f, and that's it. In the Keller case, in the non-Keller case, we don't have this in general. So To solve the equation means that there exists u, which is omega fully subharmonic, and there exists a constant c, positive, such that this equation holds. We don't know a priori which constant to choose. Tosatin-Weinkoff obtained the analog of Calabi-Yau theorem 6 years ago. In the smooth case, they showed this existence and uniqueness. For F smooth and strictly positive. And now we want to extend it to non-negative and inner field. For the color case, I sketched the proof giving 3 lemmas and 1 corollary in between. So we follow more or less the same scheme. Lemma 1 is the same as in the color case. We apply the local results to get this volume capacity estimate. As in the color case. But for lemma 2 we have to work more. First of all, we need a bit more sophisticated version, so let me state it. X is Hermitian, U is satisfying the equation. So, U solution. I'll call it star. And we need one more function, which is kind of barrier in this case, which is plurisubharmonic and bounded. And we assume that the values are between minus a and 0. And without loss of generalization, of generality, we can assume that a is bigger than 1. We fix epsilon positive. And then a bit complicated statement says that there exists epsilon naught, which depends on epsilon. And on this constant b, which I erased, but which only depends on omega. And another constant c, which depends on the dimension on omega, p, epsilon, and a, on many things. Such that for any s and t smaller than epsilon, epsilon naught, if we denote by omega epsilon as the set where u is smaller than 1 minus epsilon times v plus m plus epsilon plus s, where m, which depends on epsilon, but I will not write it down, is again the infimum of the expression u minus 1 minus epsilon v over x. Then we have something similar to the Keller case, so t to the power n, capacity of the set u epsilon s, smaller or equal to c. C is this constant here, times the Morse-Ampere operator of u over the set, set. Okay, I will write this set here. S plus 4AT. A bit more complicated. Okay. There are many constants here. What matters and what's the main difference between this and the Keller case is that again we need to take levels which are close to minimum. Here we have this minimum, and S is very small. So for those levels, we get this. I will use it several times, so I need to leave it here. And the proof is similar. I will not give it. It's similar as in the color case. We just have to replace the usual comparison principle with this weak form version A, which I gave. Now, having this, in the color case we had corollary from those two. So applying this, the same chain of inequalities, to apply the proof of corollary for omega Keller, and this lemma, of course, this version of the lemma, and lemma to H for dimension, let's say. So if we do this, we obtain the following estimate: C times LP norm of F times capacity to arbitrary power. I'll just fix the power, take it 2. One has to do some rescaling to change this into this, but it's simple. So we have this version of corollary, but then we apply not exactly the Giorgi lemma, but the proof of the Giorgi lemma. So apply proof of Giorgi to get the following estimate. For epsilon naught, which is as in the lemma here. So I recall we fixed epsilon positive, and then we got some epsilon naught. As in this lemma, there exists a constant with the same dependence as in the lemma, such that for any S smaller than epsilon naught, we get the estimate S smaller than C times LP norm of F times capacity to the power 1 over N of the set. So this is what we need for what follows. And how to get, this is the main point maybe here in these estimates, how to get L infinity estimate out of this. Let's see what we have to set. Okay, the set is defined here. In the lemma we take V equals 0. The dependence of this set on M is not clear, I mean, from the notation, but it clearly depends on M. So what we do, we fix epsilon, then we fix epsilon naught as in the lemma, and then we fix positive S, which is smaller than epsilon. So everything is frozen except for this minimum here. And now we go with minimum to minus infinity, and recall that as in the color case we also have this inequality that the capacity of the set where U is smaller than M is bounded by a constant which is independent over modulus of m, because m is here negative. So we go with n to minus infinity. So this becomes very small. This tends to 0. So this tends to 0. But then s is fixed. So for m small enough, we get a contradiction. Which means that this minimum cannot be too small. That's the L infinity estimate for the Keller case. For the non-Keller case. And now we pass to existence of weak solutions. The other problem which does not exist in the Keller case is this constant C. Because how we prove the existence having Tossati and Weintraub? What we can do is we find a sequence fj of smooth functions such that fj tends to f in Fp. And we can solve for any of those functions, and fj is positive. We can solve for fj using Tossati-Weintraub. But what we get are those solutions in J, say, and some constants. A priori, those constants can either go to infinity or to 0. And then in the limit, we wouldn't get anything. Oh, I should say that here we assume from the start that f is non-zero. One can prove that it's not very trivial that one can prove that for f equals 0 there is no solution. Okay, so the first problem is to get control over those constants. So we will prove that the sequence Cj is bounded from above and bounded away from 0. First, let me show the lower bound. Again, we use this lemma to H with V equals 0. We fix epsilon, and then we get epsilon naught, and we fix S and T, S equal T, say, smaller than epsilon. And we denote by Uj of S the set where Uj is smaller than infimum of Uj plus S. So we are again close to the minimum of Uj on this set. And by lemma 2H, we obtain that the capacity of Ujs is bounded by some constant which is independent, dependent on things but not on the functions. Cj is the constant from the equation. The norm of fj in L1 over S to the power n.